Okay, so let's just do like a quick recap and revision on what reductions mean, why we care about them, and talk. Let me try to reintroduce what 3CNFs are for those of you who've not seen it before. Then we can try to do a reduction from vertex cover to from 3SAT to vertex cover. All right. If we have time permitting, I would like to do one more reduction. Right. And it'll be like a short and sweet one. Like I think that one should be a lot easier. So like I can cover it in like 15 minutes if we have the time. All right. But that also means I need to begin now, which means I can't wait for the rest of the students to come in. If they are coming in, I assume they're not. Okay, so let's begin. Let's talk about reductions. So I think like you guys have seen some version of reductions already very early on when we talked about, I think it was mentioned during lecture that like, oh, if you want to solve a problem of like a specific problem size, let's say n, right? If you also had a solution to it with problem size n-1, you can reduce the problem from size n to solving the problem size n-1, right? Just that's just recursion in general, something along those lines. The kind of reductions that we're talking about now are actually very different. So for the most part, right, like when we've been talking about reductions in that sense, right, up till this point, like like strictly before this point, it was from a perspective of design, algorithm design. We wanted to say something along the lines of, if you can design a reduction, that could be one good way for you to solve problems, right? Like for example, with the graphs, with like the whole divide and conquer thing. It's really us saying something to the effect of, okay, I might not know how to solve this problem, but that's fine. I can always simplify it, and by simplifying it, I mean I should just reduce it to a problem that I know how to solve, right? Now you have to give you guys context, right? From like this for this week and next week, when we talk about reductions, right? It's not really coming from an algorithm design perspective. It's coming from a problem analysis perspective. Okay, so let me show you what I mean. When I have a reduction, let's call my reduction algorithm f. Why isn't it writing? Let's say I have a reduction algorithm f. So this is my reduction algorithm. Okay. There are a few properties that I care about for this. Okay, and also I should just make a side note here as a good note. Okay. For now, let's only care about yes no problems. So when I say yes, no problems, right? I mean these problems, they'll give you some input, and all you have to do is say yes or no. All right. So an example of a yes, no problem is something along the lines of, hey, does this graph have a cycle? Or is this graph a tree? That's a yes, no problem. You can solve it with DFS, right? You're given a graph, you just run DFS, and if you know that there's a cycle, you just return yes, there is a cycle. If not, you say no, there is no cycle, something along those lines. Right, so these are yes no problems. An example, a non-example of a yes no problem is sorting. Right, I give you some integers and I ask you to sort them. It'd be kind of ridiculous if your algorithm just like given those numbers says yes. Right, I know it's pretty meme worthy, but like the point is that these aren't yes no problems. Like sorting is not yes no problem, for example. Or like for example, find me the articulation point of the graph. That's not a yes no problem. Right? But if I say, for example, I give you a graph G and I give you a node V, tell me whether node V in this graph is a articulation point, and you have to say yes or no. That's a yes no problem, right? And you should know how to solve that by now. We did the whole modified DFS thing. Okay, so for today and tomorrow, right? Remember that we're only focusing on yes no problems. All right, so this is something good to have at the back of your head. Okay, so whatever I'm going to say here should make more sense. Okay, so if I have a reduction algorithm, right? There are a few properties I wanted to have, right? So for me to call this thing a reduction algorithm in the context of today and next week, okay, it's going to be that f runs in polynomial time. That's the first thing. Okay, the second thing is that I want to say something to the effect of f reduces problem A to problem B. Okay. So when I say f reduces from problem A to problem B, right, what I'm trying to say is that, like, if I should have said, how should I put this? I don't really have a good way to phrase it without being very formal, but basically, like, if I want to be intuitive about this, right, if we should be saying, okay, so given some input, let's say given input X, and when I say input X, I mean like for problem A, right, and let's say we should have said yes, all right, so, and on this input, we should have said yes. So for example, let's say you were given a graph and the graph actually did have a cycle, so you should have said yes. Okay. What you need, right, is that f on this input, right? F of this is an input for B, is an input. So this entire thing, okay? So you should think of this as transforming inputs. I take some input for some problem and I'm going to transform it to an input for a different problem. Okay? It's an input for problem B. Okay. Wait, so if this is an input, then fx is an input for problem B such that we should say yes. Right? So an example which is not necessarily true because I can't think of anything else that's like obvious enough right now. Let's say problem A is deciding whether a graph has a cycle, and problem B is whether a graph has an articulation point. Okay, like let's say a graph and some node U has an articulation with some node U and node U is an articulation point, right? For input X, your input X is going to be a graph, right? And for this problem, let's say that you should have said yes, it has a cycle, right? Then your algorithm F should run in polynomial time, and given this graph, you should transform it to potentially a different graph. It might be the same graph. The point is that you should transform the input so that this input, right, has an articulation point, something along those lines. I'm not sure if this is doable. I'm saying this is an example, right, of like what you should be trying to do, right? Like if it ever came down to it. That's one thing that you want. The other thing that you want is the opposite direction. So if given input X for problem A, okay, like for problem A, and we should have said no, okay, then what you want is that then fx, again as an input for problem B, we should have said no. Okay, so now this tells you that your reduction is useful, right? Because if I have a, so let me write down, for the sake of an illustration, let me get rid of this for now. I need some space. Okay, so what I mean by this, right, is that like for the sake of an illustration, when I say A reduces to B, what this means, let me just draw this arrow here. So I take some input X, right, and I'm going to get fx. Right? Okay. So when I say A reduces to B, so now I know that I have some function F, and function F takes an input for A and it returns me some input for B, right? And it does so with this, while preserving the yeses and the nos, right? So this is not a solution, by the way. This is just saying I can transform input A to input B. It doesn't say anything about having a solution for A or B, right? So just because I can do a reduction doesn't suddenly mean, oh, I have a solution for A, or it means, oh, I have a solution for B, right? So suppose that I do have a solution for B, right? So let's say G is an algorithm, like a polytime algorithm that solves B. Polytime algo that solves B. Okay, so think about how I can use G and I can use F to solve A. Well, one way to do it is that I'm going to take X, right? The algorithm is going to first obtain Fx and then run G on f of x, right? Because G solves for problem B and F is now technically a problem of B, right? And I know that if I should have said yes to A, what's going to happen is that the solution G run on Fx is going to give me yes, right? And if I should have said no to A, like if I should have said no to X, right, then Fx is going to give me something that G will say no to. Does it make sense? Right, so this is very roughly what a reduction is, right? And of course, the last thing is that if B has a solution that runs in polynomial time, right? So if G runs in polynomial time, I know that the solution for A runs in polynomial time, right? Because G runs in polynomial time, F runs in polynomial time, G on F runs in polynomial time. Does everything I say so far make sense? Sound off if it doesn't. Like you need to tell me now if it doesn't make sense. I'll give you guys like half a minute to think about whether it makes sense. No one saying anything? I'm going to assume this means that everyone's okay. Okay, so good. So in that case, right, this is what we call a reduction algorithm, right? And one thing to note is that you might, what's the word? Okay, so like like I said, in the context of this, we're actually talking about problem analysis. So what I mean by that is that usually when we do these reductions, right, we're not actually trying to create solutions for problem A. We're trying to show that problem B is difficult, right? So again, back to this arrow thing, right? If I reduce from A to B, right, you can think about how intuitively, if let's say A is difficult and I have a reduction F that reduces from A to B, right? You can think about how this means that problem B is difficult, right? Because if problem A is difficult and I have a reduction from A to B, right, then I cannot have a solution for B, right? Because if I did have a good solution, a fast solution for B, then I suddenly have a fast solution for A, right? So if I want to draw like a inequality that sort of like illustrates the difficulty, okay, I would draw it like this. So under a polynomial time reduction, right? If A is difficult, meaning if A has no polynomial time solution, then B should not have a polynomial time solution either. Okay. This part is kind of like super important. So try to pay attention. Now the reason why I say it's important is because like over the semesters, everyone makes the same mistake. And when I say everyone, I mean like including me, including Prof. Divesh. Like there have been classes that I've taken under him, like where he's made the mistakes, and us as students also like made the same mistake. Okay, so let me try to like nip this in the bud for you guys, because no one told me when they were my TA. Okay, when I reduce from A to B, right? Okay, this shows that A is at most as difficult as B, right? Because solving A now just becomes a problem of whether you can solve B. So if you can solve B, you can solve A, right? So when the reduction arrow looks like this, right? Note how the arrowhead is pointing from A to B. Okay, if you flip the arrowhead, you get the difficulty. All right. So again, if you reduce from A to B, just look at the arrowhead, right? The arrowhead is pointing in this way. If you reverse it, now the arrowhead looks like this, right? Look how it's flipped. Okay. What does this tell you? This tells you that A is at most as difficult as B. So if you can solve B, you can solve A. All right. But if you reduce from A to B and you have a solution for A, this doesn't say anything about B. This just says that A is easy. For all you know, B can be difficult. It doesn't contradict this inequality. All right. So this is super important. Try to remember this. The reason why I say this is because if, let's say, during an assignment or during an exam, you write the reduction in the wrong direction. All right, that's a straight 0. All right, because you will not be proving what we need you to prove. Okay. I'm only saying this because last semester, like for the last like semester and the year before that, I had to set the reduction assignment for 3230, and there were some students that actually gave me that, and the entire assignment is just giving one big reduction. So I had to give them a 0. Okay, so don't make that mistake. Okay, I even wrote in the instructions, please get the direction correct, and like I think they didn't read the instructions. Okay, so yeah, again, the arrowhead this way, A to B, you flip the arrowhead. This gives you the difficulty, right? So what does this tell you? This tells you, right, that you can say two things from this. If B is easy, okay, then A is easy. Okay, likewise, you can say the contrapositive. If A is difficult, this means that B is difficult. Okay, so think of this inequality as a notion of difficulty. Okay, so this is all there is to know about like reductions, as in like this is what we care about. Okay, and we, for the most part, what we care about is showing that when some problem A is difficult, we can reduce it to a different problem. We will conclude that problem is difficult, right? So this is for this week and next week. This is what we care about. Okay, so what was I going to show? Okay, so the first problem for the day that we're going to show, and hopefully we have time for the other one, is going to be 3SAT. We're going to reduce 3SAT to vertex cover. All right. Now, for those of you who don't know what 3SAT is, for those of you who do, this is just revision. 3SAT is basically when I give you a Boolean formula, the Boolean formula kind of looks like this. Right. And there's going to be, what we're going to do is that, wait, let me draw it out first. Okay. So these purple, sorry, like these blue parentheses here, right? Like everything in here, we're going to call that a clause. Right. Note there's an E here. So this is not like the same clause as Santa Claus. right? So this is a clause, like everything within the parentheses are clause, and within a clause, right? Within a clause, you're going to all variables together. So for an example, it could be like x1, not x3, let's say x5, I don't know, maybe x3, x10, x100, x100, and maybe over here it's like not x5, not x3, and I don't know, maybe like let's say like not x10. Maybe over here it's like x3, not x10 as well. I don't know, something like that. Okay, so within a clause, right, all the variables have an OR operator between them, and outside of a clause, like between clauses, right, it's an AND operator. Okay, and the task here, right, the task here is to find a variable assignment such that the entire formula evaluates the true. So formula becomes true. Formula, oh my god, my bad handwriting, becomes true. Right. So when I say variable assignment, what I mean is that you look at x1 and say x1 you're going to be set to true, x3 you're going to be set to true. Let's say x100 you're going to be set to like, I don't know, false or whatever. Okay. The whole point is to try to find, like, okay, not say find, but like even if you don't find it, you should at least just tell me whether it's possible or not. Right. So I want a yes no question. So the yes no question is, hey, I'll give you this formula. It looks like this, right? It's like these clauses and they are all AND together, and within the clause, like all the variables are all together. And the question is, can you find, okay, when I say can you find, I just mean like, is it possible? Do you think it's possible that you can assign the variables such that the entire formula becomes true after you substitute all the truth values that you picked, all right? So in this problem, we need to talk about problem size. Okay, I'm going to say size in parentheses because I want to talk a bit more about like what I mean by size next week, right? So like for now, there is still no issue. Next week, we're gonna spot some issues. When I say problem size here, what I care about are that there's n variables and there's m clauses. Okay, so m, yeah, so you should think about how like how you could try to think of an algorithm that runs like in polynomial time for this a solution that runs in polynomial time for this problem. It's pretty difficult, and when I say pretty difficult, I mean like people have tried for, I don't know, either something like 50 years or 100 years, and no one has solved it yet. So if you do, you can write a paper and publish it. You probably get $1 million and you would solidify your name in math history. It's a pretty famous problem. We'll talk about that next week. Right, but the problem is that the point is that you shouldn't hope to have a solution for this because it seems like there isn't going to be one. And true enough, like the most obvious algorithm that I think most of us can come up with runs in 2n times m. So it's slow, right? But the way that we would do it is that we would just try all variable assignments. You would just try, okay, let's set all of them to be true. Does that satisfy the formula? You know, then the answer might be, oh no, it doesn't. Okay, then you have to try something else, right? Then you have to go like, okay, let's try like setting all true, but this one variable to be false. You know, does that satisfy the formula or it doesn't? Okay, gotta keep trying, right? And for all you know, it's like one of the formula is like one of the ones in between. Then you have an issue, right? It's difficult. And we don't know. I mean, there are other solutions that sort of like are like smart brute force-ish, but we don't know anything that runs in polynomial time. So we don't know anything that runs in, like, for example, like even if we were say like n to the 100, like m to 1,000, right? We don't know any solution that runs in this kind of time, actually. So yeah. Okay, so when I say so now that you know this problem, right, and I want to say, okay, I want to reduce it to vertex cover, right? So in your mind, what you should think is that, what you should understand is that, okay, we are assuming that 3 set is difficult, and I'm doing a reduction to vertex cover. So what does this mean? This means that I'm trying to understand or trying to show that vertex cover is also a difficult problem. Okay, so what is vertex cover? Vertex cover is a different problem. Okay, vertex cover is a problem where you're given a graph. So let's say my graph kind of looks like this. Let's say like this. Okay, and so vertex cover, as input, you're given a graph and you're given an integer. So let's call it, I don't know, maybe the integer is, let's say like 5, I don't know. Okay, now the task, right? The task for this problem instead is that you must find at most 5. If k is 5, right, for example, then in this particular example, you can only put at most 5 vertices in some set. Let's call that set C, right? This is going to be what we call a covering set. Okay, so when a set is a covering set, what that means, right, is that you can only put you can only put at most 5 vertices in it, and this must cover all the edges. So covering an edge is what you think it is. You cover an edge if you're right next to the edge. That's just what it means, right? So the question is, okay, like for example, in this graph, does there exist a covering set of size at most 5? We can try it out. I mean, for a small graph, it's easy, right? Like you would probably need like, I don't know, maybe like 1 node here, 1 node here, 2 nodes here. Okay, so there's a cover of size 4, for example. Great. So the answer is yes, right? Given this graph and this integer value, the answer should be yes. Did I cover all the edge? Yeah, I think I did, right? Let me see. So this edge is covered. Oh, that's very big. This edge is covered. That's fine. This edge is covered. This edge is covered, right? So this edge is covered by either of these. This edge is covered by this one. 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 Yeah, okay, good. Covered all the edges. Okay, so you know, for example, if I had tweaked this value instead, like, I don't know, let's put something obvious. Let's put 1. Right? The answer is no. There's no cover for it. Right? So instead, if I set k to be 1, even if I had kept the same graph, the answer should just be no. There is no cover. Okay, so this is the next problem. And this problem, as it turns out, is also difficult. So I'll leave you to think about intuitively why that's the case. Or you can try to come up with a fast algorithm for it, and you know, like, you can think about why that's a really, really big challenge. One that is worthy of $1 million. So the thing is that, let's say that I assume that 3SAT was difficult. Can I use this to show that vertex cover is difficult? You know, this would be nice, right? Because then I don't have to cook up some proof and say, oh, you know, I'm going to show that vertex cover is difficult. Here's how I'm going to do it. You know, then you do like this very. I don't know how you would do it, right? But it's very neat that if I understand and I accept for like reality that like 3SAT is a difficult problem, and I have a reduction. Let's call that F. Right, I have a reduction that reduces from 3SAT to vertex cover, right? Then I can conclude, therefore, right, vertex cover is difficult, right? For the same reasons that I've laid out just now. That's what we're going to do, all right? So let's think about this. Like now I'm telling you your task at hand, right? What you should think about at hand is, okay, I want to take 3SAT and reduce it to vertex cover. Okay, sure. What does that mean, right? What this means is that I want to take a Boolean formula, right, that 3SAT cares about, right, which is that whole 3 clause thing. Okay, I want to take that, I want to transform it into a graph. Okay, and I want to transform it into a graph so that if my original formula could be satisfied, okay, the resulting graph has a vertex cover of size at most k, right? And k is going to be a value that we are allowed to choose, right, based on the formula, the original input formula. Okay, and likewise, if it is impossible for you to satisfy the original formula, right, it must be such that the graph does not have a cover. Okay, so let's run with that. Now, usually for these kind of reductions, I think it's kind of counterproductive to write them using pseudocode. The reason why is because for the most part, these reductions don't really have anything intelligent about them. When I say don't have anything intelligent about them, what I mean is that there is no need for you to use a Fibonacci heap. There is no need for you to use like I don't know, a UFDS or whatever, because I just need the reduction to run in polynomial time. So you can make as many iterated nested loops as you want, as long as it runs in polynomial time. Okay, so my point is that I think the challenge in reduction algorithms isn't like explaining the algorithm, giving the algorithm, like if you really know how to do it, right, giving the algorithm isn't very difficult. So I suggest that you just do it in prose, right? You just write like a few paragraphs that say, okay, for every, I'm about to show you what I mean, right? But my point is that when you pay attention to how I'm presenting the algorithm, you should take note how I'm just going to say something very simple about the algorithm. The algorithm is going to be really simple. It's like, for every variable, I'm going to do this. For every clause, I'm going to do this. And I'm going to draw some edges. I'm going to draw some nodes, right? So the reduction algorithm itself isn't very difficult to explain. The difficulty is in proving that it's correct, right? So if let's say this came off for an assignment, if let's say it came off for an exam, if let's say further down the road, you take other modules that require you to do reductions. So I think like modules like CS3230 require you to do reductions. I forgot about the rest. There are either 1 or 2 or maybe 3 modules that require you to do this, right? My point is that I think to save your effort, right, don't spend so much time explaining the algorithm, you know, because the algorithms are usually straightforward. It's the ideas behind them, like ideas that make them work, that is difficult to present, right? So spend more time talking about the proof of the algorithm, like the proof of correctness, rather than the algorithm itself. All right. So let me show you what I mean. You're gonna see the algorithm is really short. The proof is very long. Okay, I don't want to scare you guys. The proof is not very long. It's just significantly more effort than the algorithm itself. right? So let's talk about the reduction. So what do we want again? Let's refocus ourselves. What we wanted is to take a formula that 3sat cares about and turn into a graph, right? With the nice properties that I mentioned, and do so in polynomial time. Okay, so let's think about this. What should the 3CNF what should the formula look like? We know that the formula kind of looks like this. Sorry, not n, or n, blah 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 blah, and like or, right? Okay, so the first thing that I'm going to do is that I'm going to lay out all the variables. Okay, so let me just lay them out: x1, x2, x3, blah 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 to xn. Okay, so this is what my input looks like. This is what I care about. Let me make the graph. Okay, the first thing that I'm going to do is that for all xi, I'm going to write that in green here. For all xi, okay, I'm going to make dumbbells. Now, dumbbells is not an official term, all right? I'm going to draw them out on the graph, and you'll see why I say dumbbell. Okay, because on the graph, right, for every xi, I'm going to make two nodes. So what I mean is that you iterate through all the variables, okay? And if you see some variable xi, right, you're gonna make two nodes. Okay, let's say I make them like this, and I draw an edge between them. So this looks like a dumbbell, right? Like for those of you who go to the gym. Okay, I mean this is not exactly accurate, but like close enough, I guess. People in CS don't really work on the gym, so they look at this and they think, oh, this looks like a dumbbell. Well, okay, anyway, stupid joke. Okay, so what you want to do is that for every variable xi, you're gonna make one dumbbell. Okay, so the dumbbell, let's label the vertices, right? It'll be helpful for us. We're gonna call one of the sides xi. We're gonna call the other side not xi. You can give it a number if you want. That's fine. The whole point is that I need you to understand intuitively what this maps to, right? So each variable do this. So you have n. If you have n variables, you have n dumbbells. Okay, and only n. You don't have more than that, right? So it's only these, right? Draw two nodes and then draw an edge between them. Okay. Now the next thing that you want to do. Now we've done this one. What we're gonna do is talk about the clauses. So let's say for all clauses. So let's say this is clause 1, this is clause 2, this is clause 3, so on and so forth. So CI is the ith clause, right? Let's just look at the ith clause. Let's say like somewhere along the road, the ith clause looks like this. It looks like x, let's say j, xi, xj, xk. All right, and we know there's an or between them. Okay, so for all clauses, let's say the ith clause looks like this, right? Do this for all the clauses. I'm only going to show it to you for one clause, but do it for all of them. Okay. So let me draw the dumbbells that we need first. So let's say I need this dumbbell xi. I'm going to need a dumbbell xj, not xj. You're going to have all n dumbbells, but I'm only going to draw these because I have a restriction of space on my screen. Xk, not xk. Okay. Now these are the ones that you make for the variables. Now for every clause, what you're going to do is that when I see a clause like this, right, I'm going to draw a triangle. Okay. Now for this triangle, what I'm going to do is I'm going to label them. So this one, let's call it x. Oh wait, let me make it more interesting. Let's say this is the not xj variable. So what I'm going to do is that this is the not xj variable. Let's say this is the xk variable, and this is the xi variable. Okay. Now you make a triangle. Okay, for every clause. Now the last thing that you need to do, which is the part that makes everything work, is that you need to draw something called cross edges. Right, so there are going to be dumbbell edges. They're going to be okay. So this is like a dumbbell. So a dumbbell has dumbbell nodes and dumbbell edges. A triangle has triangle nodes and triangle edges. And the last one connects between the dumbbells and the triangle. So I call them cross edges. There's no official name for all of this, right? So I'm gonna draw an edge here, right? So if this clause, right, that I'm basing this triangle off of has not xj, I will draw an edge from one of the nodes to not xj. Okay. And if this node has xk, I will draw an edge from xk to xk. And if this node has xi, I'll draw a node from xi to xi. Right? Just think of it as I'm linking it to what I care about, right? I care about xi, I care about not xj, I care about xk. So I should draw my edges like that. Okay. Now of course, like I'm not only doing this for one clause, I actually have to do this for a lot of other clauses, right? So eventually at the end of the day, your reduction might look something like this. And then maybe this is like to some other dumbbell. All right. So this is roughly what it should look like. But for the sake of simplicity, I need some space on my screen, and I don't want to confuse you with the other triangles. Just note that there are going to be many dumbbells and there are going to be many triangles, right? As many triangles as there are clauses and as many dumbbells as there are variables, right? So what's the runtime of your algorithm? You only have to like make 2 nodes per variable. You have to make 3 nodes per clause, right? And the number of edges here is proportional to the number of variables and clauses. So that's just n plus n. So your algorithm runs in polynomial time, right? That's the easy part. right? Because you can just really just say, look, I'm like all I'm doing is just doing like one for loop for the variables, then there's some way to output it, then go through one more for loop for the clauses, there's some way to output it, right? So good, that's fine. Now let's talk about the more interesting part, right? The more interesting part is trying to show the correspondence, trying to show that if my original formula was satisfiable, then I have right. So one more thing, I made the graph. I forgot to output the value k, right? I have a choice over what value k should be. So I'm gonna say this is the kind of graph that I'm making, and let me just write it here on the side, like as an important note. I'm gonna set k to be equals to n plus 2m. Okay, so before I do the yes to yes thing and the no to no thing, right? I want to make a few important observations about what a set cover should look, what a vertex cover should look like. Okay, now I'm gonna use red when I color something red, right? What that means is that it's going to be in the cover, right? Just like how I did it in the previous example. Okay, so if I say, for example, if I colored it like this, what this means is that XJ is in the cover. Okay, so remember, I have n of these dumbbell nodes and therefore n dumbbell edges, right? I have m of these clause triangles. That means three triangle edges, right, per clause. Okay. Let's think about what a possible vertex cover should look like. Okay, and for now, pretend that the yellow edges don't exist. Right. So these are invisible to us. Okay, for now, right? Think about how we should go about covering the graph. Okay, and this is very important. Think about how we should go about covering the graph. So I know that every dumbbell, right, has a dumbbell edge. What this means is that the only way that you're going to cover it is if you pick at least one of the dumbbell nodes to cover, right? So it might be the case that you need to put one of these inside your cover, or you can put the other one inside your cover, right? Or it could be the case that you can put both, right? For now, let's say it could be the case that you put both. Then this would cover some dumbbell edge, right? Okay, so what do I know from this? I know that from this observation, I know I need at least n nodes to cover dumbbell edges. Okay, so what about the triangle edges, right? I can say something similar about the triangle edges. Okay, now for the triangle edges, I know I need at least 2 per triangle. Okay, so the reason why I need at least 2 per triangle, okay, is because that if, let's say I put only 1, right, think about the opposite edge, right? If some triangle has none of its vertices in the cover, you're screwed for sure, right? But if I only have 1 node in the triangle, you're still screwed because the edge on the opposite end is not covered, right? No matter how you play with the dumbbell nodes, for example, you still can't cover it, right? So we know that within a triangle by itself, right, there must be at least two nodes, right? So if I have 2 nodes, for example, let's say like this edge is definitely covered, this edge is definitely covered, this edge is definitely covered, right? The other way to do it could be that you could put like the 2 nodes here, then all the edges are covered, right? Like I hope this is obvious to you. It's all symmetric anyway. Okay. So what do I know? From this, from this observation, I can conclude that you need at least 2m nodes to cover triangle edges. Okay, but hey, if I'm only allowing a vertex cover of size at both n plus 2m, right? I've run out of allowance, right? I've run out of allowance. So what this means is that so the question now, like what I want to try to say here is this: can I ever have a triangle that has all 3 nodes inside the cover? The answer is no, I can't, right? Because if I know if I do this, right, I'm depriving some other dumbbell or some other triangle of a node that they so desperately need to cover their edges, right? So either a purple edge or a green edge is gonna be uncovered if some triangle is a bit greedier, right? This triangle says, hey, I need all three nodes to be in the cover. Then you know that some other node cannot be in the cover anymore, right? And that means some poor green edge or some poor purple edge is not going to be covered, right? Likewise, I can say the same thing, right? So like for some variable, it's not the case that you can ever put both endpoints inside the cover, right? The reason why you can't do that is because, well, if you did, again, you'd be depriving some other triangle or some other dumbbell of a node they so desperately need to have their own respective one covered, right? So the conclusion I'm trying to say here is that what you can see is that every dumbbell must have exactly one node, one of its 2 nodes in the cover, but not both. And every triangle must have exactly 2 nodes in the triangle. It can't be 3, it can't be 1. If it's 1, you know that the opposite edge is not covered. If it's 3, you know that some other edge is not, some other poor green or purple edge is not going to be covered, right? That's why I color coded these. Okay, so this is a very important observation to make, and we'll come back to it in a bit. Okay, so just bear that in the back of your head, back of your mind for a second. We'll be using it shortly. Okay, so let's go back to what we wanted to do. The original thing that we set out to do was to show that, hey, if some variable, if some formula, can be set to true, right? If there is a way, if there is some way, I don't know how to do it, right? I'm just saying, hey, assume that there is a way to do it. Okay, what should happen to the vertex? Like, we need to say that there is going to be a vertex cover that crops up here. Okay, so the intuition, right? Like if you're lost in all of this, because this might sound weird, right? We took a formula and somehow we turn a formula into a graph. What's that all about, right? The intuition, you should think about this. Like if you want like a high level like intuition perspective, what we're trying to do is to say, hey, this whole problem about solving formulas actually is really just a graph problem if you look at it in a different way. Right? I don't know if this has happened to you guys before, but like maybe you're trying to solve a problem, right? Then your friend tells you, isn't this just like this other problem? Right? Just need to look at it in a different way. So the reduction that we're doing is trying to illustrate that fact. That's the intuition, right? I know there's a lot of technical terms, right? Like, oh, the reduction needs to run in polynomial time. The yes needs to map to the yes, the no needs to map to the no. But the high level idea is really just, you're just trying to simply rephrase this problem, right? You're just trying to see this problem in a different light. And we don't want to, we don't want to make like a huge mental leap, right? We don't want to like end up having to say, oh, like this is a very difficult perspective shift. You need to like look at things in a really, really different way. That's why we want to run in polynomial time, right? Because if it doesn't run in polynomial time, it's like you need to do a lot of effort to see it, to sort of change your perspective. That's the intuition, right? Like, like I'm not sure if this helps, but it definitely did help me. It's the point is just that you're just trying to see this problem in a different light, right? Which is why we can sort of try to interpret a Boolean formula as a graph, right? Okay, so let's try to finish up the proof. We're trying to show that this reduction works, right? So let's pretend that this formula was satisfiable, right? So what does it mean for a formula to be satisfiable? It means that if no matter which clause I look at, maybe I look at like, let's pick out any clause, right? Like maybe clause 1 or clause 2, or I don't know, clause 3, whatever. Let's look at the ith clause, right? This will always work for any of the clauses. Let's just look at the ith clause. Okay, now the ith clause says that if you look at the variables, it's going to be the case that you have, like, let's say, for example, xi, xj, xk, right? Since the entire formula was true, right, this clause must be set to true, right? Somehow this clause managed to be true. The reason why this clause must be true is because you know that between all the clauses it's only ands, right? So if any of the clauses were false, right, the entire formula is false. So all clauses have to be set to true, right? The entire formula being true requires that every clause is true. Okay, so if this clause is true, let's just look at the variables and ask, hey, like if I know that you could be true, what could have happened, right? So that means that one of the variables must have, like followed the rules and been set to the correct variable, right? So for the sake of an illustration and for the sake of an example, in this case, if I had xi or not xj or xk, right, there are a few things that could happen, right? But I know that it's either at least that xi was set to true, right? So either this guy was set to true, or xj was set to false, okay, or xk was set to true. I don't know what it is, right? Okay, but the point is that what you want to do is that we need to ask ourselves, what should we include in the cover? Okay, so you know that there is going to be some satisfying assignment, right? There exists some satisfying assignment. So fine, let's talk about that. The way that we're going to put notes in the cover now, right? We know that we need to put for every dumbbell at least one note in the cover, right? Let's just put the note that we pick to be in the cover is going to be based off the truth value assignment. Okay, so if let's say that xi was set to true, let's say xi was set to false. Like I just want to make this more interesting. Let's say xi was set to false. Let's put this note in the cover. If xj was set to false, let's put this note in the cover. Okay, and if let's say xk was set to false, let's put this note in the cover. Okay, for example. Okay, so the question now is that we've actually eaten up all our allowance for dumbbell nodes, right? Because we know that any other node that we can put in the cover has to go to all the triangles, right? So let's talk about the triangle nodes. Like how should we put these so that there is still a cover, right? And you should think about the original the original 3-set problem, right? So in the original 3-set problem, right, what happens if we pick the correct assignment? We know a clause is satisfied, and when a clause is satisfied, what that means for us, right, is that some variable, let me circle that out for you here, like in this particular instance, this variable agreed with the clause, right? When I say agreed the clause, I mean like it helps the clause satisfy itself, right? So let's look at the corresponding node that we constructed for that node. In this case, it's XJ, right? So in that corresponding example, right, what you're gonna see is that like this node agreed with the clause. So this yellow edge is covered. This node, right, this node right here covers both the dumbbell edge and the cross edge. Right? This is just by definition, right? Because I know that this variable helps satisfy my clause, so this edge must have been covered. This is just because of how we constructed the graph, right? So the concern now is, okay, but what other edges do we need to cover, right? Let me mark them out in, I don't know what color to use. Let me mark them out in dark blue for you, right? So this edge needs to be covered, this edge needs to be covered, and these 3 edges need to be covered. But okay, good, we still have an allowance of 2 nodes, right? So where should we put them? Well, this yellow edge right here has been covered by a variable, by a dumbbell node, so we don't have to worry about it anymore. These 2, on the other hand, they're kind of concerning for us, right? The clause is satisfied, and I want a cover from this part of the graph, right? So what I should do is I should put this node here in the cover and this node here in the cover, right? Then you will realize that these edges are covered and this edge is covered. Right? So what about the other edges, right? This edge is definitely covered, this edge is definitely covered, this edge is definitely covered, this edge is definitely covered. Okay? So cool. So what does this tell us? This tells us that like if we know how to put the vertices in the cover, right? Assuming that there is some truth value assignment, right? When I say that, what I mean is that assuming that there exists a truth value assignment to the variables that make the entire formula true, right? Then there exists a vertex cover, right? Okay, so we've done one of the directions. Does anyone have any questions? Like, I'll give you guys like half a minute to think about whether this is confusing. Like, does what I say make sense? Because we still have like the other half to do. No one saying anything? I'm gonna assume that means that everything is okay. I'm gonna move on. Let me erase this. Okay, let's do the last part. Then we can all go home. Okay, so the last part is this. You want to show that if the formula is not satisfiable, so if I cannot find a way to assign truth values to the variables, okay, then the vertex cover, I have no vertex cover, right? Now, I don't know about you, but I find that to be really difficult to show, all right? The reason why I find this to be difficult is because you have to realize, right, that when you take the original formula and you turn it into a vertex cover problem, right, okay, that vertex cover problem like doesn't understand that it came from a 3-set formula, right? Which is why, for all you know, right, there could be covers that work like this, right? And intuitively, if you think about this, you can't really translate this back to a 3-set problem, right? 3-set, like interpret this under 3-set, right? Because if right, like I had a vertex cover that looks like this, what can you say about the variable xi? Like, should it be set to true? Should it be set to false? I don't know, right? We know that when we were moving from yes to yes, right? I said, okay, if there is a truth value assignment, we will just follow what the truth value assignment says, right? Because we know that intuitively we can sort of like correspond the truth value assignment to the choice of the node, right? But when we're moving like, you know, like from like, you know, saying it's not possible, you have to say it's impossible for you to have a vertex cover. You can't just say like at face value, you can't just say something like, oh, you know, like let's just focus on all possible covers that look like, you know, that look like something like this. Like every edge has like one. Every dumbbell has like 1 node and like every triangle has 2 nodes. You know, you can't just say that, because for all you know, the vertex cover, like there is a vertex cover that doesn't follow your rules, right? Then your proof doesn't apply. Which is where the previous 2 observations that I made come in very, very handy for you, right? So using that line, right, you would say, okay, you know, we're going to use these 2 observations to argue that, okay, every dumbbell must have exactly 1 node, every triangle must have exactly 2 nodes. So any cover, any potential cover must always look like, you know, like two nodes on the triangle and I don't know, like one node on the dumbbell each, something like that. Okay, so still, I think in general it's very difficult for you to show the no implies no direction, because there's always a lot of cases that you need to take care of. So I propose for you personally, from my own experience, that what you do is the opposite thing, But I mean, the opposite thing is that you try to show that if there exists a vertex cover, there must exist a satisfying assignment. Okay, that's how I prefer to show it. Okay, so let's do that. Let's do that. Oops, sorry, 1 second. So the way that we're gonna do it is what we're gonna do. Right, so we want to show the yes from so I want to do contrapositive. So I want to say yes to vertex cover, right? Implies yes to 3 set. Okay, so assume that there is a vertex cover, right? Based on the observations that I laid out to you, we know that this means that every triangle, there's going to be exactly 2 nodes, and every dumbbell, there's going to be exactly 1 node. Okay, so for example, maybe it looks like, perhaps, right? For example, it looks like this. I don't know. Okay, so what observations do we need to make now? We need to say that every triangle edge is covered. Good, we know that that's going to happen always. And every other dumbbell edge is going to be covered. Good, we know that happens always. Okay, now the concern is only the yellow edges, and the yellow edges, right, tells you whether the clause is going to be satisfied or not, right? We assume that there's a vertex cover, so we know that all the green edges are taken care of. That's fine, right? And because we assume that there's a vertex cover, all the purple edges are taken care of. That's fine. Okay, and because we assume that there is a vertex cover, right, we know that this means that all the yellow edges have to be taken care of as well. And that's the important part to take note of, right? These are the ones that we're really stressing on. Now, what do I know? I know that in a triangle, right, I'm only allowed two nodes, right? So what that means for us, right, is that if you look at a triangle, right, for all you know, the 2 nodes look like this, right? The whole point is that it can only cover 2 of the cross edges, right? And the last one has to be handled not by a triangle. It has to be handled by a dumbbell. Like, as in, like, it cannot be handled by the triangle itself. It has to be handled by the other side, right? It has to be handled by the dumbbell, right? Since we assume there's a cover, what we can say then is that because this triangle does not have the edge, the node to cover it, it must have been covered by the variable, right? Okay, so in other words, what I'm saying is that since there's a vertex cover, at least one of these yellow edges must be covered by a dumbbell node, not a triangle node, right? I hope the drawing makes it obvious. Okay, so we have made this observation. Now we can just bring this back to 3 set, right? So what would I say? I say that I know that every node, every dumbbell pair, right, like has exactly 1 node on it. So if the node that we picked was the true node, then we just set the corresponding variable to be true, right? If it is the false node, we set the corresponding variable to be false, right? Then someone might ask you, but how do you know this satisfies all the clauses, right? So then you say, okay, let's just take your word for it. Let's just look at any clause. Let's say let's look at some triangle. That triangle, let's say, was made because of CI, right? We know that CI made this triangle. Okay, and we need to say that picking the truth value assignments this way satisfies this clause. Okay. So why does it satisfy this clause? Well, we know it satisfies this clause because, like I said before, one of the yellow edges, right, one of the cross edges must have been covered by a dumbbell node, not by a triangle node. What does this mean? This means that the corresponding truth value was set to the correct one that the clause needed, right? This clause needed to see true on xi, which we gave it, right? Because we set it to the correct value, right? It agrees with the clause, right? I mean, like, at least one of them agree with the clause. It could be 2, it could be 3, we don't know. But in the quote unquote worst case, right, only one of them do. Okay, so what do we know? We know that this clause must be satisfied. It must be satisfied. Right. So the existence of a vertex cover, right, maps to a satisfying assignment. That makes the entire formula true. All right. So that concludes the proof, right? The algorithm runs in polynomial time, right? If the input formula can be satisfied, can be set to true somehow, right? We know that there's a vertex cover for it, right? And we know that if there is a vertex cover for this this graph that we make, right, then there must be a satisfying assignment that satisfies the original formula. All right, does that make sense? Like, this is basically the entire proof. All right, so I'll stick around if you have questions, but if not, class is over. I can see you guys next week. Anyone have any questions? If not, then everyone's just gonna be like, I feel like most people are just here waiting for other people to have questions. Then everyone is like deadlocked. Like, if this is a distributed system, everyone just waiting on each other. and no one's asking anything. So then like everyone's just sticking around. So okay, do you guys get it? I'm very worried you guys don't get it, because this is like one of the most abstract concepts you will see in 3230, if not the most. Concern increases. No one saying anything. You know. Kind of get it. All right. Well, if you need time to process, that's fine too. This is recorded, so you can always refer back to it. All right. If you have a question now, I'll stick around. I don't know. I'm free now, so I'll just stick around till like in case you guys are free and you guys have a question to ask. I'll be here.
So if all the clauses cannot be satisfied, then the purple triangle cannot cover the yellow edges, right?
That's right. You don't even have to say for all, right? As long as at least one of the clauses cannot be satisfied, you know that at least one of the triangles cannot cover the yellow edges, and the dumbbell nodes will also not cover the yellow edges, right? So think about what it means when a clause is not satisfied. So let me get rid of these, right? So what happens if a clause is not satisfied? So when a clause is not satisfied, then all of your variables must have gone the opposite direction, right? So when I say opposite direction, I mean like, oh, I need xi to be true, but xi was set to false, right? I need xj to be false, but I set it to be true, and I need xk to be true, but I somehow set it to be false, right? So think about what the dumbbells look like. The dumbbells should look like this, right? Like the opposite thing happens, right? You're always moving away from the yellow edges, right? And I know that in the triangle, right, I'm only allowed 2 nodes, right? So no matter all the yellow edges now need to be covered by the triangle. So you have an issue because no matter how you arrange the 2 nodes, you can arrange it like this, you can arrange it like this, right? Or you can arrange it like this. No matter how you try to put the 2 nodes, right? The point is you're screwed. You're screwed for good because you cannot cover all the yellow edges in time. There will always be one hanging yellow edge that is waiting to be covered, and it will never be covered. Right?
Okay, yeah. So the triangle is not the covering of triangles is not dependent on the dumbbells?
Yes.
Okay.
All right. You should think of the triangle nodes, right, are really just there to make sure that as long as one of the yellow edges is satisfied, right, covered, right, you can cover the other two. It's sort of like, because like you think about how this is OR, right? So OR means that like, oh, you can be like, if I have, for example, OR of 3 things, you can think about how the entire thing is true. It could be the case that like only one of them is true and then like the entire thing becomes true, right? Or it could be the case that 2 of them are true, then the entire thing is true, or 3 of them are true and the entire thing is true, right? The point is that the intuition here is that you should not really be punished, right? If like, for example, let's say this yellow edge was correct, let's just say correctly covered, right? Then there should be a cover, right? You shouldn't say, oh, you have to cover all yellow edges using the variables. That's not true, right? You only need one of them to be true, right? So the other 2 like triangle nodes are just really there to sort of make up for it, right? As long as the variables are responsible for covering one of the yellow edges, okay, it's fine, bro. I'll cover the rest, don't worry.
Okay, right.
Right, cool.
Thank you.
No worries. Does anyone have any other? That was a good question, by the way. Like, I think in the previous class they asked it as well, but I forgot to account for that in this class. The ones that you should care about really are the dumbbell edges. The triangle edges are just there as like an allowance. You should think of it as like a quote unquote allowance, right? So as long as one of the yellow edges is satisfied, okay, don't worry, the triangles will fix up the rest for you. And this is exactly what it means to satisfy a clause. As long as one of the variables is satisfied, who cares what the other 2 are? You shouldn't care, right? So that's how you should see it. That's right. Does anyone have any other questions? I mean, like, I'm free, so I'll just sit around and wait. Because if not, you guys can go. It's not completely fine. Then we'll cover like other different types of reductions. I mean, not say other different types of reductions. We'll cover like reductions from different things next week. So this reduction was from a Boolean formula to a graph. Next week, we'll talk about from a set of numbers to a set of numbers, and we'll talk about one that is from a graph to a different graph. Do I have one from a graph to a set of numbers or from a set of numbers to a graph? I do, but they're very difficult, so I'd rather not do it because it will take too much time. All right, good. I think like hopefully no one else has any questions because no one said anything. Let me stop the recording now.